Alright, so this is our Honors Chemistry Section 8.4 lesson video, Part 5. Oh my gosh, I didn't think we were ever going to make it here. So we're going to continue on with a little bit about hybridization, but we're also going to talk about sigma and pi bonds. And I don't know about y'all, but I'm kind of glad to be getting to the end of this. I love this stuff, but sometimes making the lesson videos just is a little exhausting. Alright, so when we're looking at hybridization, if you watched the previous video where I showed you how the electron configuration changes to make the hybridization happen, when you're asked a question about it, usually they're not going to focus on that. They just want to know what is the hybridization. And that part's super easy. It's totally based on the electron domain shape. So if the electron domain shape is linear, it would have sp hybridization. If the electron domain shape is trigonal planar, it will have sp2 hybridization. And if the electron domain shape is tetrahedral, then it will have sp3 hybridization. And notice I'm saying the electron domain shape, not the molecular shape. So notice I didn't say anything about bent or trigonal pyramidal because we're only focusing on electron domain shape when we discuss hybridization. Alright, so let's look at an example together. So it says, indicate the hybridization of orbitals employed by the central atom in NH2 negative. So first, let's draw the Lewis dot structure to figure out its shape. So N has 5 valence electrons, H has 1 times 2, and then plus 1 for that negative charge. So we have 5 plus 3, which is 8 valence electrons to work with. My single atom goes in the middle. I'm going to bond everybody, and then I got to make everybody stable. So hydrogen only needs 2. Alright, so I have my structure. I'm allowed 8 electrons. I have 2, 4, 6, 8, but I can tell this is not going to be a linear molecule because of the lone pairs. Okay, it's not going to be linear. It's actually going to be tetrahedral. Okay, well, by its domain shape. Alright, so remember, we can draw our molecule like this if we want to, and then of course we need to bracket it and put our charge. So that at least I can keep it all in the same plane. So remember, yes, the molecular shape is bent, but the electron domain shape is tetrahedral. Since there are 4 electron domains, that makes it sp3 hybridization, because there are 4 hybrid orbitals, s and 3 p's. And so it's super easy. Knowing why the hybrid orbitals happen and how they happen, that's the tricky part. Being able to identify it is all based on shapes. Now, if you're having trouble with shapes, if you have no idea where I got the tetrahedral and the bent from, you need to go back to section 8.3. That's when I discuss Vesper theory shapes. Alright, so maybe pause it and you try this one. So it says, predict the electron domain geometry and the hybridization of the central atom in SO3 negative 2. Alright, so you got to predict the electron domain geometry and the hybridization. So I'll assume you've paused the video and tried it, so let's look at it together. So S has 6 valence, O has 6 times 3, and then I add 2 more for that negative 2 charge. Alright, so we have 18, 20, 26 valence electrons to work with. So I'm going to put my single atom in the center, so I'm going to put my S in the middle, make everybody stable. And again, if you struggle with Lewis dot structure, you need to go back to section 8.2. The faster you get at Lewis dot structure, the easier this whole chapter is. Alright, so I got to check my total. I'm allowed 26 valence. I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. But I can see there are 4 domains. So this is going to follow tetrahedral shape again. Alright, so I'll put my S in the middle. I'm going to put my valence on top. I'm going to put 1 O coming down, 1 O coming out towards y'all, and 1 O that goes back into the board. And then of course, because I have my charge, I'm going to bracket it and put the charge. So it asks for the electron domain shape, so your electron domain shape is tetrahedral. Now if it had asked you for molecular shape, which it did not, but if it did, remember you can't see the lone pair. So you would just see the tripod at the bottom, and that's called trigonal pyramidal. But it asks for electron domain geometry. And then it says, what's the hybridization? Well, since again, there are 4 domains. Remember, this is electron domain, not bonds. 4 domains means 4 hybrid orbitals, which puts the hybridization at sp3 again. So if it had been linear and there was 2 domains, it would be sp. If it had been trigonal planar and there was 3 domains, it would be sp2, because that has 3 hybrid orbitals. And since there's 4 domains here, it is sp3. So hopefully you got that one right. Like I said, really drawing Lewis dot structure and getting those shapes is just super important for a lot of the stuff in chapter 8. So next let's talk about what happens when we got multiple bonds. Because how does all that overlap in the middle? So a sigma bond, which sigma symbols right there, is a bond that occurs when a line that passes through the 2 nuclei of the bonded atoms also passes through the middle of the orbital overlap. So see, I can draw a line right here, and the orbital overlap happens right in between the 2 nuclei. The same thing happens right here. My orbital overlap happens in that line. The same thing happens here. My orbital overlap happens when I draw a line between the 2 nuclei. However, there's another type of bond called a pi bond. And hopefully you already knew the symbol for pi, but it's there if you did not. A pi bond is a bond that occurs when the overlap of the orbitals is perpendicular to the internuclear axis. Don't let that word throw you off. It's just the line we draw through the 2 nuclei. In a pi bond, the overlap occurs above and below. So these are examples of sigma bonds. So see, when we draw the line, the overlap is occurring on the line. On a pi bond, it's happening like this. So instead, like for a sigma bond, we would have our 2 p orbitals overlap like this. And so you can see how the overlap right here, I'm going to put them a little closer just so you can see the overlap better. The overlap is right in between the 2 nuclei. A pi bond looks like this. So you can see there's actually no overlap between the 2 nuclei. You have an overlap above and below. That is a pi bond. Okay, and so then here's some examples of pi bonds down here using P and D. Now notice S will always have to overlap as sigma. That's its only option. So unlike a sigma bond, in a pi bond there is no probability of finding the electron on that internuclear axis. So here we have a sigma bond right here, and so the electrons are right in between the nuclei, and then we have pi bonds happening here. And I know you can't see the overlap, they didn't draw it big enough, but we have pi bonds happening here, and so the electrons would have to be above or below that internuclear axis. So since the p orbitals in a pi bond overlap sideways rather than facing each other, the total overlap in a pi bond tends to be less than in a sigma bond. This means that pi bonds tend to be weaker than sigma bonds. So again, let me just show you kind of what I mean there. So like when I have my 2 atoms like this, I can get good overlap. Okay, see, I can get a lot of overlap. Hopefully y'all can see that in the video. But when I'm kind of coming from this angle, remember, we can't get the nuclei too close together. When I come in this way, I'm only getting a lower amount of overlap. And so because of that reason, your pi bonds tend to be weaker. Single bonds are always sigma bonds. And then a double bond, one of the bonds is a sigma, and the other bond is a pi bond. So what happens is, and again, I know this picture is a little overwhelming. You have a sigma bond right here. You can see this kind of goldish color, yellowy orange. And then you have a pi bond right here. That makes your double bond. Okay, so you have 1 sigma and 1 pi. And here's an example of it kind of moving together. So you can see you have your sigma in the middle. So see, our sigma bond comes together right there. That makes up 1 of the double bond. So there's our sigma bond overlap. But because there is a second bond, it can't go in the same location, so it's a pi bond overlap. And so you can see how that overlaps too. So in a multiple bond, one of them is a sigma and anything else is a pi bond. So let's look at what a triple bond looks like. A triple bond consists of 1 sigma bond, so again, you can see that one right here, and 2 pi bonds. So you can see these are kind of like in an X formation. And so we have kind of an overlap here, and we have an overlap here. And so it looks kind of like this. So you have your 1 sigma and your 2 pi bonds. So since pi bonds occur using the unhybridized p orbitals, it can only occur with sp and sp2. because sp3, there aren't any extra p orbitals left over. All right, so just in a multiple bond, one is a sigma and the rest are pi bonds. So our next one says formaldehyde has this Lewis dot structure. Describe how the bonds in formaldehyde are formed in terms of overlap of appropriate hybridized and unhybridized orbitals. All right, so I can look here and I can find C. I can see it is a trigonal planar structure, so I can see that C is going to have the hybridization because it's trigonal planar of sp2. All right, it's going to have sp2. So I can see that here is one of the bonds, here is one of the bonds, and here is one of the bonds. So it's going to have 3 bonds formed with sp2 orbitals, and those will be sigma bonds. All right, so these 3 are going to be sigma, but we also have a multiple bond. So it will also form 1 pi bond with the unhybridized, because notice we're only using 2 of the p orbitals, with the unhybridized p orbital. Okay, so it's going to form 3 sigmas with those hybrid orbitals, but then it'll form a pi bond with that unhybridized p orbital. So if they had asked me how many sigma, how many pi bonds, I would have said 3 sigmas, 1 pi. Remember, in a multiple bond, one of them is always a sigma. The others are pi's. All right, so maybe pause the video and try the next one. It also has a part B and C. So look at those. I'll assume you've done that, and now we'll look at it together. So it says, consider the acetonitrile molecule. So we have that right here. Predict the bond angles around each carbon atom. Well, y'all, I can look at this carbon atom and see there is a tetrahedral arrangement. I'm just going to call this C1 and C2, just so y'all know which ones I'm talking about. So C1 would have bond angles of about 109.5 because we have a tetrahedral shape. I can look at my other C and see that it has a linear shape because there's no lone pairs. Because remember, sometimes they'll draw it flat, but it's really not flat. Well, in this case, because there's no lone pairs, it literally has to be linear. And so even though this electron domain is much larger, this electron domain can't get any further apart. So it has bond angles of about 180 degrees. All right, so we're still going to use the same Lewis dot structure for our next couple of questions. I'm going to click and see what the questions are, and then we'll come back to this one. So it says, describe the hybridization of each carbon atom and then determine the total number of sigma and pi bonds. All right, so let's look back here. So again, C1, C2. Around C1, because it's tetrahedral, 4 domains, there will be sp3 hybridization. So this goes with part B, not part A. It's just on the next slide. For C2, because it is linear, it will have sp hybridization. Okay, so don't count this as 4 domains. This is only 2 domains. This one just happens to be a huge domain. All right, and then part C says how many sigma and how many pi. So my sigma bonds are all single bonds, so 1, 2, 3, 4, and then 1 of a multiple bond. So 1, 2, 3, 4, 5 sigma bonds. And then pi bonds are any other bonds in a multiple bond besides the first one. Because remember, 1 is always sigma. So I would have 2 pi bonds. So that's my answer for part C. So hopefully you got those right. I always get super excited when I see questions like this because I know they're really easy. And so hopefully everybody's getting them. So the last thing we need to talk about is what's the difference between localized and delocalized bonding. So localized electrons belong to the 2 atoms that form the bonds. They're going to stay in those overlaps between those 2 atoms all the time until the bond is broken. However, we know resonance structures exist where sometimes we kind of draw the double bonds here, but they could also go here. So what's going on with that? Like, how is it sometimes here and sometimes here? Well, remember, we said resonance is like a hybrid. So when resonance structures exist for a molecule, the electrons move around and are considered delocalized because they're not in a specific location. So whenever resonance is possible, that's when you have delocalized pi bonding electrons. So it says, describe the bonding in the nitrate ion, which is NO3 negative. Does this ion have delocalized pi bonds? All right, so first thing is I need to draw it, of course. This is why Lewis dot structure ability is very important. So N has 5 valence, O has 6 times 3, and then I add one more for that charge. So I have 18, 19 plus 5, which is 24 valence electrons to work with. So I'm going to put my single one in the middle. I'm going to go through and make everybody stable. I'm allowed 24 electrons. I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. So I have 2 too many, which means I need an extra bond. However, I could put it in any of the 3 locations, so I do have hybridization. Resonance. Once you realize that, to answer this question, you could actually stop. But I'm going to finish and draw the correct 3D structure and everything before we answer this question. All right, so I go back and alter to get everybody back down to an octet rule, and so I can see now I would actually have a trigonal planar arrangement, and I have 3 possible options of how I could draw this. So I'm going to go ahead and draw all 3. So I could put my double bond here. And remember, the single bond oxygens have 6 lone electrons, whereas the double bond oxygen has 4. So that's how you can know to move everything around. And then, of course, because it has a charge, I'm going to bracket and put my negative charge. All right, so once I see this, I see, yes, there is a pi bond, and yes, it is delocalized because it can move around. So it says, does this have delocalized pi bonds? I would put yes for that. All right, it also says describe the bonding. So if you wanted to describe it, you could talk about hybridization on the N because it has 3 electron domains. N has an sp2 hybridization, and it forms 3 sigma bonds with those orbitals, and then it forms 1 pi bond, which of course, now that we can see it has resonance, it's a delocalized pi bond. All right, and so that's all you have to do for the delocalized. It's really easy. You just need to look, if it has resonance, it's delocalized. Those electrons can move. If it doesn't have resonance, then it doesn't have any delocalized pi bonds. So just because something has pi bonding doesn't necessarily make it delocalized. All right, so next it says, which of the following molecules or ions will exhibit delocalized bonding? See, a question like this, if you're not good at Lewis dot structure, could literally take forever. So you've got to get where you can draw Lewis dot structures really quickly. Now on here, because I literally just need to know if it has delocalized pi bonding or not, once I can even tell there's resonance, I'm not going to necessarily finish the Lewis dot structure. Like, I'm not going to draw it 3D. I'm not going to draw all the possible resonance structures because that's not what the question's asking. So once you can tell it has resonance, you just circle that one and move on. Okay, so save yourself some time if you're on a test. If it's not asking for those structures, you don't have to officially draw them perfectly. All right, so let's just start with SO3. So I'll put SO3 over here. So S has 6 valence electrons. O has 3 times 6 for a total of 24 valence electrons. I'm going to put my single bond in the middle and then make everybody stable. I'm allowed 24. I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. So I am going to need a double bond. But because I can put it multiple places, I can automatically tell right now it has resonance. So again, because it doesn't ask me for the 3D shape or anything like that, or the resonance structures, I'm not going to sit there and waste time drawing all of them. All right, so that's one of them. Now notice it doesn't say which one, so I do need to check all of them. All right, so next we have SO3 negative 2. So S has 6, O has 6 times 3. I'm going to add 2 more for that charge. So I have 18, 20, 26. Now, technically, hopefully you can notice that if we had just had 2 extra electrons here, we wouldn't have needed the double bond. But say you couldn't figure that out. I put my S in the middle. I make everybody stable. And so I'm allowed 26. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. I don't need any multiple bonds. I am going to at least put my charge, although technically you don't have to because it's not asking about that. So this does not have any delocalized pi bonding because it doesn't have resonance. So then we just move on. So that one's not one. We have H2CO. So H has 1 times 2 plus carbon has 4 plus oxygen has 6. So 10 plus 2 is 12 valence electrons. All right, so for this one, it's going to follow this shape right here. And so again, in class, if you needed some help with that, I would be glad to help you set it up. All right, so I make everybody stable. So of course my H's just need 2. My O is going to need some more, and my C is going to need some more. I'm allowed to have 12. I have 2, 4, 6, 8, 10, 12, 14. So I need an extra bond. So I'm going to put my extra bond, adjust for my octet, and this is what I get. Now before you think, oh, it has a double bond, it has delocalized pi bonding. Every time there's a multiple bond, it doesn't necessarily mean delocalized pi bonding. It's only if it has resonance. I can't put a double bond to hydrogens. So this is the only spot to put it in. See, over here, I could have put it between this S and O, between this O, between this O, but here I can't put a multiple bond to hydrogen. So this one also does not have resonance. Okay, that's important to note. Like, don't just assume, oh, there's a multiple bond. It has delocalized pi bonding. Not all pi bonding is delocalized. All right, so our next one is O3. So O has 6 times 3, which is 18 valence electrons. So I'm just going to bond them in a row. Remember, shape is not important on this question. I make everybody stable. And then I'm allowed 18 electrons. I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. That means I do need a double bond. I adjust for my octet. And then I can see that clearly I could have put the bond over here. So this one would have delocalized pi bonding. And like I said, I'm not going to draw the resonance though because that's not actually part of the question. All right, and then our last one is NH4 positive. So N has 5. H has 4 times 1, and then I'm going to subtract 1 because of that positive charge. So 9 minus 1 is 8. I'm going to put my single one in the middle, which is my N. Bond all my H's. Everybody's stable. I'm allowed 8, 2, 4, 6, 8. I'm going to bracket and put my charge, although that's technically not necessary for this question. And I can see there's no pi bonding at all, much less any delocalized pi bonding. So that would not be one of my choices too. So remember, the important thing is don't just look for pi bonding. You have to look for pi bonding that can move through resonance structures. All right, so we are done with chapter 8. I know it's overwhelming and it's a lot of information. The main 2 things, like if you only get, the main 3 things, if you only get 3 things out of chapter 8, you need to be able to draw Lewis dot structures well and quickly. You need to know those Vesper shapes, and you need to know intermolecular forces. So those are the 3 most important things out of chapter 8. Although all of it's important, but if you only can have time to learn 3 things, Lewis dot structure, Vesper shapes, and intermolecular forces. So we are done with chapter 8. You made it.